Okay, finally, we have arrived at differential equations. And for most people who take this course, this is probably the subject that they actually were wanting to learn about. It turns out that there is some overlap between the things, well, there are things from linear algebra that are really helpful or in fact absolutely necessary to know in order to solve certain kinds of differential equations. So that's the reason that it gets packaged up this way. Just before I leave linear algebra though, can I just say that if you really want to be very good at linear algebra, you should do one of two things. Number one, take a real course in linear algebra, a whole semester. We've got a third of a semester on this subject. And so naturally, we just blast through it and sort of hit the high points, don't explain too much, skip virtually all of the theory. It's because there's nothing else I can do and have anybody learn anything. And even at this, I always feel guilty about this time in the semester because I think there's all this stuff I should have told you and I didn't. Well, I didn't because there wasn't time. But for instance, there's a whole field that's opened up over the last 20, 30 years called data science. And you can make a pile of money doing data science, and a lot of it has to do with linear algebra. A great deal of it has to do with the parts of linear algebra we didn't discuss, although it's related to the things that we did discuss. So I'll just tell you, if you got this far and when you generally understand what's going on, you have got enough information that you could take like that little blue book that I recommend in the syllabus, Anton, and you could probably just read it. You understand enough now that if you work through that, start working exercises, you probably will do fine. And having done that much, then you could, with profit, start reading things where somebody says, hey, look at this cool thing we can do with linear algebra. For instance, the singular value decomposition, which I didn't even mention until this moment exists, turns out to be quite useful in data science. But if you just read another book, you'll have understood enough that you could then read about the singular value decomposition and it would make sense to you. So you really do need more if you want to use it very much. But I did give you enough that you'll be able to get through the stuff that we'll use for the rest of the course. And it's better than nothing. So with apologies, I move on, even though there's so much more I should say. So today we're going to start talking about differential equations, and we talk about ordinary differential equations, which we will explain in just a minute. First thing we need is a bunch of vocabulary. So sorry, but if we don't know what these words mean, we just can't communicate with each other. So what is a differential equation? A differential equation is one that involves one or more derivatives of a function. And this is really different from what we've done up till now in the course, for which the function is the unknown quantity that we're trying to solve for. So for instance, here, I cooked up a couple ahead of time that I could then find the solutions for. So x squared y double prime minus 5xy prime plus 5y equals 15. That is a differential equation. Now, how is this so dramatically different from anything we've done up till now? Well, up till now, in this course at least, we've been solving equations where, let me pop one up here. When you compute the solution are numbers. So, give me a solution to this system of equations. Well, we could set s and t equal to 0. x1 is minus 1, x2 is 0, etc. They're fixed numbers are what give us the solution to the equation. Here, you're looking for a function y. that will satisfy this equation. So you start with a function, take its first and second derivatives, plop it in there, do all of the algebra, and it's supposed to come out and say 15 equals 15 or the equivalent. Okay, so that really is different from what we've done before. Here's another one, y double prime plus 2y prime minus 3y equals 0. This is another example, and the goal is to find a function, y equals f of x, that satisfies that equation. Now, here I've taken ordinary derivatives, and by that I mean it's like y is a function of x, y is a function of t, something like that. And if, say, y were t squared, then the derivative would be 2t, and the second derivative would be 2, and the third derivative and a higher would be 0. But you could have a function of more than one variable, in which case you would be taking partial derivatives. So here's another one. And I'll just say, we mentioned these right at first, only because we're going to say we're not doing any of these. So these are ordinary differential equations. This is a partial differential equation. Take the second partial derivative of f with respect to x twice. Take the second partial of f with respect to y twice. Add them up, you're supposed to get 0. Okay, so what's a solution look like? Well, a solution should be a function. So on this first one, give it a name, 1, y equals x to the 5th plus 3 is supposed to work. And we could test that out probably. Y prime equals 5x to the 4th. Y double prime equals 20x cubed. And now what would happen if you plug this function and its derivatives in up here? Well, you notice at this point, that pattern kind of becomes clear. I had x squared times the second derivative, x times the first derivative. Well, that's kind of undoing a lot of what a derivative does to a power of x, right? It knocks the power of x down by 1 every time you take a derivative. So we're pumping them back up with these coefficients of x squared and x. So if I take this, and whoops, this, y double prime, and I multiply it by x squared, I get 20x to the 5th. And if I take minus 5x and multiply it by y, well, I would get minus 25x to the 5th. So 20 minus 25, now I've got minus 5 x to the 5th. And then if I take 5 times y, then I get plus 5x to the 5th. That all cancels out. But I'm left over with 5 times 3, which is 15. Sure enough, this will fulfill that pattern. Likewise, the second one, y equals, let's see, e to the minus 3x, I think we'll do. Y prime would be minus e to the minus 3x, and y double prime would be plus 9 e to the minus 3x. And everything in sight's got an e to the minus 3x on it, so you just got to pay attention to the coefficients. Y double prime, we get 9 minus 2 times 3. 9 minus 6 is 3. Subtract another 3, sure enough, you get 0. So this works for that equation there. So for equation 2, here's the solution. For equation 1, here's the solution. These derivatives were just for convenience. The solution to the first one is, or a solution to the first one is x to the 5th plus 3. A solution to the second one is e to the minus 3x. And this one right here, well, I'll give you a few solutions, and you will think I'm playing games with you. How about this? F is always 0. If I take its second derivative with respect to x, sure enough, I get 0. Take its second derivative with respect to y, oh, that works too. And so I get 0 plus 0 is sure enough 0. There's a solution. So could I think of something harder? Sure. All right. f is 3x plus 5y minus pi over root 2. All of this is just eye candy. When I take the second partial of f with respect to x, I get 0. When I take the second partial of f with respect to y, I get 0 again. And 0 plus 0 equals 0. Did I turn the recording back on? I think, yes, I did. Finally, well, here's one that's not trivial. Will this one work? Okay, sure. Take the second partial of f with respect to x. The first one would be 2x, second partial would be 2. And the second partial with respect to y, first one would be minus 2y, second partial with respect to y would be minus 2. So this would become 2 minus 2 equals 0. Well, finally, we've got something that's not completely silly, right? So this one, f equals x squared minus y squared, does in fact solve this, and it's not in a silly way. It's a real function, and it has some interest to it. It describes a surface, as a matter of fact. It's sort of like a parabola in two different directions. So if you go, let's say if you got your x and y axis, along the y-axis, it opens in a parabola downward. In the x, it opens upward. And you get a saddle point here in the middle. And there's all kinds of, you can find those pictures on the internet easily enough. And they do look kind of cool. Okay. Well, let's see. What's the difference between ordinary and partial? Ordinary means ordinary derivatives. So this one is ordinary, and this one is a partial differential equation. People tend to refer to ODEs and PDEs, partial differential equations and ordinary differential equations. This course is about ordinary differential equations, so we are leaving these for now. There is a field of study, partial differential equations. They're tremendously important in physics and engineering. So don't think that we're skipping them because they're unimportant or because no one knows anything about them. It's just that you really need to learn the ordinary differential equations first before you understand the discussion for the partials. Let's see. I already said that. So let's skip to the next page. The order of a differential equation is simply the highest order of the derivative, the highest order derivative that occurs in the equation. Now, I want to write down a couple of examples here because it would be really easy to get this confused. So let me write this one down. X, y double prime minus 3y equals 0. This is a second order differential equation. Now, I say that it would be easy to get this confused because somebody might look at this and say, well, everything is just to the first power. So this looks like what I used to call first degree. And, you know, in some way of thinking that that's true. But that's not what order is talking about. It looks at the order of the derivatives. So it's a second derivative, so it's second order. In the same way, this one is still second order. You see, whoops, I wanted a 3 here. You see a 3 in an exponent, but it's irrelevant. It's the derivatives that we're looking at. So both of these are second order equations. Most of what we will look at in this course are either first or second order differential equations. As a matter of fact, most of them are second because we'll sort of dispatch the first order pretty quickly. And if you think about it, you already know how to solve a bazillion first order differential equations. If I told you this, y prime equals 3x minus 5. What's y? Well, you learned this in calculus, right? You just take the antiderivative. It's 3/2 x squared minus 5x plus any constant. So what's the solution to this differential equation? Right there, you get it by taking an antiderivative. And so you can see from this example, it's hard to make first order equations get really complicated and still be able to solve them. They tend to fall into the categories of pretty easy or utterly impossible. So we don't spend that much time on them. We do some, but not a lot. Now, there's also the concept of a linear ordinary differential equation. And let me just mention that this one here and this one here are both linear. And this tends to cause some confusion right at first, because people look at this and they say, what do you mean it's linear? I see an x cubed in here. That's clearly not a linear function. Well, it's not a linear function in x, but with respect to derivatives, it's linear because you have derivatives only occurring to the first power and the original function. That's the 0th derivative. So these are both linear equations. A linear equation has to be expressible this way. It's perhaps a function of x times the, good heavens, I never caught that before. These are supposed to have parentheses because they're derivatives. This might not be a linear function of x, but then you have the nth derivative of y, plus some other function of x, might not be linear with respect to x, but then it's just the n minus first derivative of y, etc. So we say that stuff like this and how do you solve this? I have absolutely no idea. Okay, this one is linear. Why? Because I have a second derivative, but it occurs to the first power. I have a first derivative, but it occurs to the first power. I have the function itself, but it occurs to the first power. This is linear. Something that looks much simpler this is nonlinear. Why? You can't possibly write it in this form. Functions of x times a derivative of y to the first power. You can't get rid of this second power without creating another problem. You could say this, well, it's plus or minus the square root of y double prime equals y. Now I've fixed the y. Yes, you have, but now you've got this one to a 1/2 power. So, this is nonlinear, even though it looks relatively simple. And this one, even though it's ghastly complicated, it's nevertheless, it's linear. And that matters. Linear functions, linear differential equations are oftentimes solvable without too much trouble. Okay, a solution of a differential equation is a function. Typically, we end up calling it y. In this class, it doesn't have to be. You could call it x or f or something like that. And once in a while, we will. So let's zoom in on this particular differential equation right here. Y double prime minus 9y, and see if we could find its solutions. Well, you could just notice, first of all, that the 0 function would satisfy this, right? Second derivative of the 0 function is the 0 function. multiply the zero function by -9, you get the zero function, so that would solve it. So y is identically 0 is a perfectly good solution. It's not a very interesting one. Well, I don't know. Can anybody think of a non-trivial function y that would have this property? If you take if you take two derivatives, you get the original function back, but it's multiplied by -9. Did I get one? Okay, let's try it. E to the, yeah, it's so close. It's so close. It's good insight. I like it. By the way, if you want to learn some mathematics, you can't be afraid of guessing wrong. So try something. So we've landed on a very useful property here. If I take the first derivative, I get -3 e to the -3x. Then when I take the second derivative, I get another -3. Whoops, lost my x there. And then that turns out to be 9 e to the -3x. However, this really does tell me something. This one, I've got the pattern y double prime equals, say a is a positive number. Then minus a y is one pattern, and plus a y is another pattern. And you have solved this one. E to the e root a times t is going to solve this class of equations. This solution and it could be plus or minus, doesn't matter. So for instance, if I want a 9, I put a 3 up here, right? So you did actually get a nice solution here, but unfortunately it's for a different problem. So what has this pattern when you take two derivatives, a negative sign, you sort of wrap around to something like you started with, but a negative sign pops out. You all know. I could, however, then I would have a negative on this side and on this side. So it would sort of be this sort of thing where, you know, you could then simplify it out. So good guess, but that would get us back to another way of looking at this.
Log, natural log?
Okay, let's think about log. When you take a derivative of log of x, roughly speaking, you get 1 over x, right? Then when you take a second derivative, you start with x to the -1, so you get minus x to the -2, 1 over x squared. Now we got the minus. However, you're comparing log of x to 1 over x squared, different functions.
Right.
Yeah, so good thinking though. You got a minus and that's useful. Cosine. Take the derivative of cosine, you get sine. Take the derivative of sine, you get almost negative cosine. So with two derivatives, if you start with cosine, you'll bounce back to cosine, but you pick up a negative number. So it looks like y equals, oh, look at this. Those two equations are different. I changed in midstream. Let's stick with the one we started with, okay? If you put this on the other side, it becomes a plus, right? Oh, this is buggy. I didn't read this one. I was too busy grading. Okay, so the solution, a solution to this one could be, well, we think a cosine would work well. Because if I take a derivative of cosine, I'll get minus sine. Derivative of minus sine will give me minus cosine. That gives me the minus. What is the argument in here? Cosine of what? Just like cosine of t won't work. Because that would give me, its second derivative will be minus cosine of t. And I don't have the 9. 3, yeah. Yeah, 3 theta, 3t, 3x, whatever you like. I'll go with x, I guess. Why? Just to be different. See, if I don't say something different from you, then you'll think, this guy's contributing nothing. So I said, yes, theta would work, but so will x. And just to spell it out, first derivative of cosine is minus sine. And off the screen here, second derivative is minus 9 cosine 3x. And sure enough, if you take the second derivative and add 9 times the original function, this and 9 times this, you do indeed get 0. I'm going to suggestively label that y1. Anybody think of another function that would have this property? Sine, I like it. Sine of 3, I didn't hear what you said. Of something, oh, okay. We'll be consistent with x, I guess. Yes, this would certainly work. Plus 3, cosine 3x is the first derivative. And second derivative, cosine of 3x has derivative minus 3 cosine of, or rather sine of 3x. So minus 9 sine of 3x. Now, it turns out that there are infinitely many solutions. And you can get the others from these. Can you think of another one? Would the zero function work? Yes. Yeah. Now, could we somehow get the zero function by doing some arithmetic to that? It's really simple. You knew it in high school, probably before. This is so much fun because I know the answer to all the trick questions. So even though as a student, I might well have been desperately confused, I now can feel intelligent and not only that, smug. So, well, if you multiplied it by 0, you'd get another solution, right? What if you doubled it? Would you get another solution? 2 cosine of 3x. Would that be a solution to this y double prime plus 9y equals 0? Yes, because you just pick up a 2 on the second derivative and the original function. So how about 5? Could you multiply by 5? Would that work? Well, you all have figured out the pattern by now, I'm sure. So if you take any constant, let's say C1, times cosine of 3x, plus any other constant times sine of 3x. Am I on the screen? Oh, pretty close. So for instance, 5 cosine 3x minus 17 sine of 3x, that would be a solution. So, and it turns out that's all there are. Anything that is a solution can be put in this form, but you know that it's not obvious from what we've said so far. So there are some differential equations and there are some solutions, and we're going to be working with these things for a good long time. There are also things like called initial value problems and boundary value problems. Let me give you an example. Let's suppose we had this, y equals C1 cosine of 3x plus C2 sine of 3x. And then we're also given these conditions, y at 0 is equal to 5, and y prime at 0 is equal to 3. You can use these initial, they're called initial because they, conceptually, it's at time equals 0. It's at the beginning. Of course, it doesn't really matter that this is 0. If these were both 7, it would still be considered an initial value problem. We just started timing as time 7. So, and what really matters is that this argument and this argument would be the same. You can make some progress here. We know that if we plug in 0, we'd get, well, the cosine of 0 is 1. So that's C1 times 1 plus C2. The sine of 0 is 0. And that's equal to 5. If I took the first derivative, I'd get 3C1, whoops, minus 3C1 sine of 3x plus 3C2 cosine of 3x. Whew, what a mess. And then y prime at 0, well, the sine of 0 is 0, so that thing just drops out entirely. But this one, 3C2 times 1, the cosine of 0 is 1, that is equal to 3, telling me C2 must be 1. And this one tells me that C1 must be 5. Therefore, I think I've just got room to squeeze it in here. The y that we are looking for is this. It does fit this pattern, C1 cosine 3x plus C2 sine 3x, but C1 is 5. Plus C2, that's 1. So that is an example of and these are initial conditions that have been added here, and this is called an IVP, or initial value problem. Now, you could just have the value at 2 different places. So instead of describing things about y and y prime, you could just describe the value of y at 2 different places, as 0 and say pi over 2. And I don't know, we're a little short on time, so I probably won't work that out. But you could do a similar thing here by plugging those in. Don't worry about it for now. When it comes up, and it will come up, I will do plenty of examples. Okay, last thing in here, oh, good heavens, is many pages of talking about direction fields, modeling, and qualitative solutions. Let's take this differential equation right here, pretty simple. Can anyone think of a solution to this? The derivative of the function is equal to itself. E to the x, I like it. There's another one, having listened to me now, that you probably think of this immediately for all problems. What? Constant, would that work? One constant will work. One doesn't work. 0. The 0 function, I wonder if that works, yeah. So, by the way, you don't want to say this too many times to your mathematical friends, because after a while they get a little put out and they say, okay, we want to find all non-zero functions that satisfy this equation. So, but it's not just completely silly either. We should be aware of the fact that oftentimes the 0 function will work, or sometimes it's specifically, it will not work because it appears like in a derivative. I mean, a denominator, another D word, but it means something totally different. So if you have 1 over y equals something or other, well, then the 0 function doesn't work. Okay, so sure, e to the x would be a solution to this. As a matter of fact, you could have 5 times e to the x. That would also work, right? That 5 just rides along. And I'm going to write this one down. E times e to the x, that's just a constant, right? But the reason I'm writing it is because you could then say it's e to the 1 times e to the x, which is e to the x plus 1. As a matter of fact, this one you could do the same thing to. It's e to the log of 5. So it turns out that all of these guys, any constant, c e to the x, can be written in this form. Let me call that C1. that is equal to either plus or minus e to the x plus some other constant, C2. And how do you find it? You take a logarithm. But it doesn't matter, because what I want you to see is all solutions to this differential equation can be written in this form: plus or minus e to the x, and then you could have plus or minus a number up here. Because after all, this C2 could be negative, right? So subtractions could work. Now, to save some time, I typed in some examples ahead of class. E to the x minus 3, e to the x plus 4, minus e to the minus x, minus e to the x minus 3, and I'll just graph them. That's what all these things look like. They look like the function y equals e to the x, and then you just slide it right or you slide it left, and you're also allowed to flip it over. Now, you did this in Calculus 1 until you were sick of it. You thought to yourself, if my instructor asked me one more stinking time to find the slope of the line tangent to the curve at x equals something, I am going to scream. And then he asked, and then you did scream, but you felt better, right? So it was okay. Now, the point I'm trying to make is we could draw little line segments next to these curves, right? And if we put a whole bunch of those solution curves and put a whole bunch of those little line segments, I'm giving you the short version, you would get a picture that looks sort of like that. These little line segments, these are tangents to the to a solution curve, because all of them look like y equals some constant times e to the x, so that either shifts left or shifts right, and it may flip it over. And by looking at these line segments, you can sort of see what the solutions look like. They come along the x-axis, and eventually, you know, might be to the left or right of the origin, but eventually they sharply diverge either in the up or the down direction, right? So the idea is, if you could just do that much, you could see something about the solutions. And so that's saying, if you could figure out the slope at, and maybe I should write it that way, slope at xy. If you could just come up with some kind of a formula for that, even if you couldn't solve the equation by using techniques of algebra and calculus, you could still see something about the solution. So why would you care? Well, suppose you started with this, a pendulum. And I usually have one in the form of a charger for my computer, but I didn't bring my computer. But you know what this is. It's like a swing, right? It swings back and forth. And by the way, if you push it hard enough, it'll flip around maybe once or twice or 3 times. And then because there are frictional forces at work, then it'll start swinging back and forth like that. Now, I'm going to skip all this because we just don't have time for it. And to tell you the truth, it is not that important right now. The calculus and the algebra doesn't matter so much, but you start with this, you write down a differential equation that describes it, and you get something like this. Then you say, well, I don't know really what to do with that, because that's second order differential equation. The slopes of lines come from the first derivative, right? So could we somehow get this to a first derivative? Well, you pull an old trick, which you can find out by reading this. It is directly related to this first order equation. So now you could dy d theta, that's the y prime. You could say that's equal to minus k sine theta over y. Now, I wrote it here somewhere. Oh, I wrote it on this. If you read the details, you would find out that this really is y prime that's being measured here. So it's velocity. It's not distance. It's velocity in the upper direction, so that's just a negative velocity down here. And that's the theta. That's how far this thing has rotated from its initial position of hanging straight down. And when you see this, of course, I guess it's not such a bad thing that I've got two of these. And I make it work. This goes on forever. There are lots of them. So it just goes on forever and ever. This, in a certain way, because what we're looking at is velocity on the y-axis, the up and down axis, and angle to the right and to the left. In a certain way, that's not that helpful, except you can see this. You're expecting, in some cases, to get a periodic solution if things just keep moving around the circle. And in other ways, it could be periodic like this. And then there are things that are almost sort of linear up here. But that has to do with velocity, not position. Well, if you think about it now, you got a string, you got a weight on the bottom here, and you give this thing a good push. If you push it hard enough right at first, it just spins around, right? And its angular velocity is pretty much constant. And that's the sort of thing. Now it's going up and down in the sense of positive and negative here, but nevertheless, the angular velocity would remain, let me see, that description is way up here, something fairly positive. On the other hand, if you get it into the spot where it's like a swing, I mean, a child sits on, and you're not a evil, depraved person, but you're a nice person, you put the child on and just give them a little push, you don't want to make children go. It's bad. So they're just swinging back and forth gently, having a good time. And if their mothers were watching, even the mother would be having a good time. Okay, that's a critical part of the description of this problem. Then, where was I? I'm having so much fun with the joking, I forgot. In that case, you have a periodic kind of solution. Now, all of that makes sense with the physical situation, right? And you could actually sophisticate this a little bit, and you can put in a term for frictional forces. And then, now, by the way, nobody does this by hand. It's way, way, way too hard. You use a computer program. MATLAB actually has a routine for this. And then you start seeing solution curves that look like this. Now, keep in mind, we're not looking at position and vertical position and angular position. We're looking at something else. But you can nevertheless see that these curves are in some way decaying to some steady state solution. And they could decay to this place, and you could guess, and you'd be right, that there's infinitely many of these attractive points along the horizontal axis. And if you think about the physical situation now, that's actually true. If you took a real world pendulum, so now we have frictional forces, give it a good hard push, well, it might zing around the circle a few times, but eventually it's going to do this and decay, and finally, practically speaking, it comes to rest, right? So that's what you're seeing in here. The point of that is that even if you cannot solve the differential equation, if you can come up with these direction fields, it is really, really handy at times. It gives you information about the character of the solutions. We're finding points of attraction here. So some kind of a steady state solution as time goes on. Now, the reason I tell you that is I double checked it before I came here today. It's still up. There's a website. There's probably a bazillion of them, but I did a Google search and I found this one and it worked fine, so I put it in the notes. So in the homework, it asks you to make some direction fields. Well, what you do is you download the live version of this from Blackboard, and then you can just click on this link and it will take you right to right to the website. And all you do is you type in, okay, what's your formula for the derivative? It's minus x over y, and you click go, and boom, it draws direction fields for you. So it's really good to get some experience with these. I'll just tell you ahead of time, it's virtually impossible to test because you can't do them in a hurry by hand. But it's nevertheless good to play around with it. So that's what I would suggest that you do. And that's mostly what, this is just getting oriented. You know, how would you solve this differential equation? Well, its derivative is x squared. You take its antiderivative, right? So x cubed over 3 plus a constant. And I have 3 minutes, so I have time to tell you one last story. This really happened. In high school, I learned this equation that you all learned in high school physics too, right? The position of an object is 1/2 its acceleration times the square of the time plus the initial velocity times the time plus its initial position. And I remember why I thought that, well, in some ways it's good thinking for an ignorant person. I thought, boy, are these physicists stupid? Why don't they just redefine that A so that it doesn't have a half in there? But then when I got to calculus, I found out, oh, if y, its second derivative is equal to a constant A, then if you go back to the first derivative, you get AT plus some other constant, which we might as well call V0. And then if you take one more derivative away, you get 1/2 AT squared plus V0 plus yet another constant. Now, the reason I tell you this story is, first of all, to point out that ignorance is not always bliss, but also to remind you that when you start doing all of these differential equations are like that. You just take some antiderivatives, okay? So when you do that, don't forget the constants because they actually are really important, right? So, whoops, you've seen all this before. All right, and then next week on Tuesday, we'll get started for real with differential equations, and I think you'll like it. At least I do. It's a fascinating subject. See you next time.